Hello, and welcome back to our Topic 3 on Power Series in AP Calculus BC. This is our third day of this topic, and yesterday, or last class, whenever you were here, we were introduced to the idea of a Taylor polynomial. Today we're going to be introduced to a second type, really a subset of Taylor polynomials known as Maclaurin polynomials, and then we're going to finish class with analyzing terms of different Maclaurin and Taylor polynomials. To begin, though, we're going to look at the idea of an odd versus an even function. And I know with the way last year has been, and honestly the way curriculum has changed over the last few years, a lot of you may have never heard of an odd or even function. These are definitions that go thrown around a lot in upper mathematics and not as much in lower mathematics, though they're totally understandable to really anybody in Algebra 1 and up. So what I'd like you to do is to take a few minutes and decide what makes something an odd function versus an even function. And it asks you to give 3 reasons why those adjectives are used to describe the trig functions sine of x and cosine of x. But really, if you can just understand 3 different reasons that odd and even are applied to functions, that's a good way to go. All right, hopefully you took some time to do that. I think I'm not going to go too far into what makes something odd or even. I'll give you 2 quick reasons for any function if you'd like, and then we can move on to our actual lesson. So, let's start with an even function. We know that, well, we know based on above that y equals cosine of x is even. And there's 2 quick ways to test if something is an even versus odd function. The first way is to look at a graph, right? And cosine starts here and looks something like this, and then finishes over here. We say that something is even if it has symmetry about the y-axis, which means I can take this part of the graph and fold it on to this part of the graph, right? This point will fold over on here, this point would fold over onto here, and so on and so forth. The second way, and the more common way to test if something is an even versus odd function, is we take 2 x values, a positive version and its negative version, and we substitute both of those into a function and see what we end up with as a result. Okay, so let's try that right now. Let's try maybe x equals pi over 4 and x equals negative pi over 4. Okay, so if I wanted to substitute both of these in cosine, cosine of pi over 4 is square root of 2 over 2, and cosine of negative pi over 4, remember your unit circle negative pi over 4 moves you backwards, and cosine is the x, so cosine is still positive there, so that's also positive root 2 over 2. We took a positive, plugged it in, we took the negative version, plugged it in, we got the same positive answer. Let's go ahead and compare that to sine of pi over 4. Sine of pi over 4, sine's the y value, that's positive root 2 over 2. Sine of negative pi over 4, now we're dealing with the negative y-axis, so sine has to be negative root 2 over 2. This is the idea of a negative, or I'm sorry, an odd function. But let's finish off with that even function first. Essentially, the definition I think they give you for an even function, right, is that an even function, if you do, and they say f of x equals x, and f of negative x equals, actually I think they do it like this. They probably say f of x equals f of negative x, right? So they're saying the output of a positive x value is equal to the output of a negative x value. And isn't that true? That's what we saw over here. That's the idea of an even function. Versus what we did over here, and this is always phrased kind of strangely for me, they say something like f of negative x is equal to the negative of f of x. And that's a little bit harder for me to understand. You can kind of play around with those negatives too if you want to make it a little different. But essentially what this is saying is if you substitute a negative x value, and a negative x value isn't actually the right way to think about it. If you substitute in, let's start with this one. If you substitute in an x value, you will of course get an answer. That answer will be the opposite of the opposite x value that you plug into your function, which is really a mouthful. Essentially, they're saying that if you plug in a positive and you get a positive. Then when you plug in that negative version, you'll get the same answer, but a negative version. However, and then this is where things get a little bit weird, and maybe it's easier to show with another even function, x cubed, right? If I plug in, no, that's another bad example, drat. That's okay. Essentially, if I had plugged in a negative and gotten a positive here, then when I plug in a positive, I'll get a negative here. So they're telling you that you get, essentially, if you make the interior the opposite, then your answer is also the opposite of the other answer. There, that's what I was trying to say. Go me. Even versus odd. Well, that's two ways, and I guess I didn't talk about the graph of sine, so I should probably pretend to be a good teacher. The graph of sine starts here. Looks something like this. Ooh, wavy, wavy, very exciting. We say that these ones have diagonal symmetry, and actually it's much easier to see with the graph of y equals x cubed, right? Where y equals x cubed looks like this. Okay, and can you see that symmetry here and here? Well, you'll see the same symmetry here and here and all the way through, right? So this guy over here is going to map to that one over there, and so on and so forth. You have that diagonal symmetry. Now that's only two reasons why we use that even and odd notation or even and odd vocabulary. I'm actually going to give you a third one in just a second, and this third one's actually my favorite. So here we go. A Maclaurin polynomial, it's our new definition, is a Taylor polynomial centered at x equals 0. Right? Now remember, Taylor polynomials can be centered anywhere. We did a few last class. We compared e to the x centered at x equals 0, and we compared that to e to the x centered at x equals 1. Both of those are Taylor series, are Taylor polynomials. However, any Taylor polynomial centered at x equals 0 is more commonly known as a Maclaurin polynomial. Now, you are required to know 4 Taylor polynomials by heart, but really, they're actually all Maclaurin polynomials. They're all centered at 0, which is really nice. The first, of course, is that e to the x we were just talking about, and you should remember it's Maclaurin polynomial. Why don't you go ahead and write it down right here. First couple terms in general term, please. Cool. Hopefully you got something like this. Nice reminder of our pattern, because we're going to see this general pattern in just a second. And then I always like to go up about 4 terms, give or take, and then x to the n over n factorial. Nifty. Now, we're actually going to learn 2 more of the 4 Taylor Maclaurin polynomials that you're going to need to know by heart. And the next 2 are, non-shockingly, cosine and sine. So we're going to go ahead and derive the Maclaurin polynomial for each of those, and then see if we can find the general term too. And that one's a little bit trickier. So you ready? Let's jump into it. We said we're going to call this g of x, I guess. All right, so we're going to need a couple derivatives here, and I said I like to go out at least 4 terms. So let's take a look at the first few terms here. So we have g of x, which was cosine of x. G prime is that negative sign, right? Derivative of anything starts with a c is negative. Second derivative is negative cosine. Third derivative is cosine becomes negative, but there's already a negative there, so I think those turn into a positive sign. And then our fourth derivative, oh cool, that's back to cosine again. That makes life really nice, and it shouldn't shock you that these trig derivatives have a cycle of 4. Cosine, negative sine, negative cosine, sine. And then they repeat. Cosine, negative sine, negative cosine, sine. Right? And it's always going to be that pattern. You might just start somewhere else. So now that we have the fourth derivative, we actually know derivatives 4 through 7, right? That'll be the same as 1 through 3, and so on and so forth. Let's look at, we're doing this at 0, I think. It's a Maclaurin polynomial, yeah, so g of 0, cosine of 0, which is 1. G prime of 0 is negative sine of 0, which is negative 0, so 0, that's cool. G double prime is negative cosine of 0, cosine's 1, but negative 1, and the third derivative, g triple prime, g prime prime prime, is 0, and then we're back to our starting point again. So I could write this out as cosine of 0, but we should already see that it is 1. Look at that pattern. 1, 0, negative 1, 0. 1, 0, negative 1, 0. Cool. Pretty quick, pretty easy. Let's go ahead and do our general Taylor, or in this case, Maclaurin polynomial. We're going to call it q sub n of x, and this is going to be, we're using g here, so g of 0 over 0 factorial times x minus 0 to the 0th. First derivative, x minus 0 to the first. Again, the more you write this, the more it's going to cement into your brain. You need to know it. It is the lifeblood of our Taylor or Maclaurin polynomials. All right, that looks pretty good. I changed that 3 to or 0 to a 3, which was strange. Don't forget, you're always looking for that trifecta, that little triangle that goes through to match, and then you've got your little matching right there, your dual. Okay, plugging things in. G of 0 was 1. This is just x to the 0th. All right, the next one is 0, x to the first. The next one's minus, so minus 1 over 2 factorial, and I'll keep those factorials in there. I guess it's not going to hurt for now, is it? Over x squared plus 0 over, what is this next one? Did I miss a negative somewhere? No, I'm just being silly. 0 over, this is our third derivative, so 3 factorial x cubed, and dot, dot, dot. Okay, well, simplifying this out, actually, I think things get a little bit weird here. This is 1, and actually, I think the whole first term just becomes 1. The next term becomes 0. Huh, well, that's weird. And then the third term is 1 over 2 factorial x squared. The next term becomes 0 again. But I think that's actually already enough to see the pattern. We went positive, negative. I think the next one has to be positive. And we were 1 over 2 factorial. This has to be 1 over 4 factorial x to the 4th. And then I think I should have done better with space here because I actually want to do one more line. So I'm going to move over to the right. Sorry about that. And let's see if we can get this done a little bit more simply. 1 over 2 factorial x squared plus 1 over 4 factorial x to the 4th. Can we see that pattern? Positive, negative, positive. Next one's got to be negative. And then so on and so forth, right? We just alternate. And there's a few things to note here. First, look at every exponent. Every exponent is an even number. And that's interesting. You might actually want to explore that. It doesn't work with all functions, but it's interesting with trig functions. You'll notice that cosine is an even function, and all the exponents show up even. Well, sine's an odd function. I wonder if all the exponents show up as odd. But I'm not quite done yet, because we do need that general term, and the general term here is a little bit tricky. We need to be good at writing patterns, but oh my gosh, we are good at writing patterns. We just spent a lot of time doing that. And actually, I'm going to do this one more time, sorry. I'm going to write this as x squared over 2 factorial just a little bit more succinctly, just so I can see everything together. We don't really need all those ones up there thrown off our formula. So what is our formula? Well, we know it has a fraction. That's exciting. Make it do the fraction over here. Looks pretty good. We know it's x to some power, and we know there's a factorial. But let's just see. It looks like this guy over here is x to the 0th over 0 factorial, right? So looking at this, maybe we can just do n and see what happens. Well, we're going up by 2 every time, so we know that has to be 2n, right? We learned before that's our slope of the exponents. And then you have a couple options here. You can assume that you're starting at the 0th term. And that actually makes this really easy, because if n is 0, that turns to 0. We can make this 2n factorial, plug in 0. Cool. If we plug in 1 to get our next term, right, we substitute in 1, then I think that one matches. And yeah, actually, life is pretty easy from here. That is our general term almost. But what did we forget? Oh yeah, we're alternating in sign, but we know how to throw in an alternating factor. We've done it in every unit so far. We just need that -1 to the nth. And then we want to make sure that's right. If we substitute in 0, our 0th term, that becomes positive. If we substitute in 1, that becomes negative. Yeah, I think that looks really good. All right, let's go ahead and actually, if you want to write this down, this is the second of the 4 Maclaurin polynomials that you do need to memorize. This represents cosine. And before we jump over to sine, we should actually make sure we did this right. And one of the easiest ways to see if we did this right is to graph cosine and graph the Maclaurin polynomial we just found and see if they are the same graph. So here we go. I have cosine ready to go. We're going to go ahead and graph its Maclaurin series, which as a reminder was x to the 0th over 0 factorial, right? That's 1. Minus, we always alternate. We went positive, now it's minus x squared over 2 factorial. And that actually matches pretty well so far. That's exciting. That's just a parabola. Okay, so then plus x to the 4th over 4 factorial. Oh, that's looking even better. Look at that. It's kind of molding down on it. And then minus x to the 6th divided by 6 factorial. And look at that. We are doing a really nice job. We can go further to continue out the pattern. Plus x to the 8th divided by 8 factorial. And you can see we're doing better and better. In fact, this is another one of those Maclaurin series or Taylor polynomials, Taylor series, that will eventually, if you put out an infinite number of terms, it will perfectly match onto cosine. It will be exactly the same as cosine. So you can start to see this use. Instead of finding, say, cosine of 2, just plug 2 in for all the x's here, and now you found cosine of 2 without having to use cosine. It's pretty wild. All right, so we've done well there. Why don't you guys go ahead and try to find sine? This one is not too bad. It's so similar to cosine. Remember what I said about that even odd, and then once you've tried it, come back together and we'll see how you did. Alrighty. So working with sine, and I'll switch colors from what I did up above, we are going to see that same pattern. I think I used h to represent sine up above, so we have sine of x. H prime is going to be cosine, of course. The second derivative will be negative sine, and the third derivative will be negative cosine, and that makes my fourth derivative equal to positive sine, which is back where we started. It's that same cycle, but the cycle is offset by, well, where is that one? That's down here. It's offset by 3-ish or so derivatives, which is kind of interesting, right? We took 1, 2, 3 derivatives, and that brought us over here. So that odd number of derivatives really is going to change our Taylor polynomial, our Maclaurin series. So let's rock and roll. We know, and I think we can do a little less math here, that h of 0 will be 0. H prime of 0, sorry, will be 1. And 0, 1, can you see the pattern? Now it's going to be negative 0, and then negative 1. And then it starts over again. 0, 1, negative 0, negative 1, and all that fun stuff. Let's get to our t sub n of x, and we'll do this one in purple. Going a little bit quicker. Okay. Writing out the pattern. The first time I do it, I always write out the pattern. You've got to be perfect with this pattern. We use it every day for the rest of this semester as I mess up literally every single term. Very proud of me right now. There we go. Now we've got it. We're in the groove. Cool. And so on and so forth. So t sub n of x. Well, notice that actually this first one is 0. So it becomes 0 over 0 factorial x to the 0th. The next one is plus 1. Right? And so this is, going to be our plus 1 here. Just making sure I didn't make any mistakes, but I think this is okay. Plus 1 over 1 factorial, x to the first, minus 0 over 2 factorial, okay, times x squared plus, nope, this one's minus, isn't it? Minus 1 over 3 factorial, x cubed, so on and so forth. Well, does the same thing happen as before? And I'm going to leave extra room this time because I know I'll need a fourth line. Look at me learning from my mistakes. Well, this whole first term becomes 0. This is just x to the first over 1 factorial. Next term becomes 0. Next term is x cubed over 3 factorial. I think we have that exact same pattern, right? I think my Taylor series for sine is x to the first over 1 factorial minus x cubed over 3 factorial. And notice the alternating sign again. Positive, then negative. Okay, and then we're going to go positive and negative, aren't we? So nothing too bad. Looks something like this. So it's going to be plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, dot, dot, dot. Look at that. We have all odd numbers here. How exciting is that, huh? All odd numbers as we go through. Sine is an odd function. And if you can remember that, it honestly helps a lot of my students to remember the pattern of this Maclaurin series, right? Odd function, so it has to start with an odd exponent. The same way cosine is an even function, so it has to start with an even exponent. We always start with the 0th power anyways, so it's just like that Taylor polynomial. Positive, negative, positive, negative. Very cool. General term, x to the 2n over, leave some space here, over 2n. But if we plug in 0 here, 2 times 0 is not 1, right? So I think we need to add a 1 on here, and then we should be good. If we substitute in 0, 2 times 0 is 0, plus 1 is 1. Cool. 2 times 1 is 1, plus 2 is 3. Also cool, and so on and so forth. So 2n plus 1. It alternates in sign. Same idea. Negative 1 to the n. Plug in 0, and I think we're doing just fine. Look at that. General terms, we're crushing it, guys. Really well done. Now, you may have noticed, oh, sorry, this is the third that you do need to memorize. All right, now you may have noticed that I'm going back and forth between saying Taylor polynomial versus Taylor series. They mean the same thing, and I will go back and forth, but we never formally defined it. It is very common to refer to these as infinite Taylor series, and we touched on it a bit last class, and it shouldn't shock you. It's infinite because we need to go in infinite ways to make it perfectly match sine, and actually we should make sure it's matching sine too, huh? So why don't I graph that while I'm talking? And it's a series because we're summing up each term. In fact, we're going to get back to our friendly friend sigma in the next couple of classes and see how we can work that in to our Taylor series. So Taylor polynomial, Taylor series, same idea. And Taylor series really shows that it's going to be a subset of those power series that we'll introduce in a couple of classes. But let's see if we did sine right. So we'll turn these two guys off. Here is sine. How do we write it out? Well, we know it has to start with an odd power, so x to the first, divided by 1 factorial, and it always alternates in sign. So minus x cubed, oops, divided by 3 factorial, right? It's looking pretty good so far, plus x to the 5th, divided by 5 factorial. Look at that, it's doing really nicely. Minus x to the 7th, divided by 7 factorial. Oh yeah, we're doing so well. What if we had gotten the signs wrong? What happens then? What if this was a minus, and then a plus, and then a minus, and then a plus? Oh, it's exactly backwards. This, of course, would be the Maclaurin series for negative sine. Oh, yeah, because you just multiply through by a negative, huh? So, yeah, I think we did everything really well here. I am proud of all of us, mostly me because I always screw up on this, but definitely you guys as well because this is super cool. We can definitely see we found the right Maclaurin or Taylor series for sine centered at x equals 0. Okay, the second part of today is about analyzing terms of Taylor series, and they really like to throw one of these at you for multiple choice questions, and they're honestly not a terribly tough question, but it does take a little bit of critical thinking. So a commonly asked question is, they're going to say, you have a Taylor series. Tell me about the coefficient of the Taylor series term that has a degree of 7. And you have to know what makes up that 7th degree term. And so, although you can write out the entire Taylor series, it's generally faster to know that pattern, right? Where, especially this pattern right here. So if they ask you about a degree of 2, then you just need to write out what the degree of 2, what the term with a degree of 2 looks like, and you'll be well on your way. For example, let's examine the third term of the Taylor series, right, where we have our first term, second term, third term, and that is a little tricky, right, because it's the third term, but it's a degree of 2, because technically our first term is a degree of 0. So it shouldn't shock you that, I'm saying that a lot today, that's okay, that these two pieces, all right, or rather this third term is always going to be 1 less than the term number. So if it's a term of 3, then we know that it's going to be a second degree term. So we need to notice that the coefficient of this term, and I'm going to highlight the coefficient right here, is made up of 2 pieces, a numerator of f double prime, a numerator of f double prime, and that's awkward, a denominator of 2 factorial. And again, each of these numbers right here are 1 less than the term number. Now, let's take a look at a couple examples and see how that helps us. So let p of x equal that crazy looking polynomial, and it's going to be the 5th degree Taylor polynomial for some function f. F is doing its own little windy thing, and they said, ooh, we can make a polynomial match this windy thing. Cool. So then they said, and it's centered about x equals 0, what's the value of the 4th derivative of f at 0? Well, that's tough because you're looking at this and you're like, oh, well, I don't know the function f. We know p of x, but that's not the same as f, right? It's an approximation for f. So if we can't take 4 derivatives of f and then plug in 0, how do we do it? Well, that's easy. We take the 4th degree term of the Taylor polynomial, and remember how the 4th degree term is set up. The 4th degree term was found by doing the 4th derivative evaluated at 0 divided by 4 factorial of x minus 0 to the 4th, right? Once we did all the calculations, the answer came out to 7x to the 4th. So I'm actually going to show that. I'm going to show that this is equal to 7x to the 4th once all calculations are said and done. And we can actually clean this up a little bit too, I think. The 4th derivative of 0, 4 factorial. We can do 4 factorial, right? 4 times 3 times 2. 3 times 2 is 6. 6 times 4 is 24 times x to the 4th has to be equal to 7x to the 4th. Why don't we divide both sides by x to the 4th and get rid of that? So that gives us, I think, then that the 4th derivative at 0 divided by 24 has to equal 7. Multiply both sides by 24. 7 times 4 is 28. Carry the 2. 14, 15, 16. I think we have now found that the 4th derivative of f evaluated at 0 is 168. So a very clever type of problem that really counts on you knowing how this is set up, right? And you should also note, let's see what happens. Let's say that you're like, ooh, I think it's this equation right here. I think I just have to take 4 derivatives and then plug in 0. Does that work? I don't know. Let's find out. So we have p of x equals 3x squared minus 5x cubed, 7x to the 4th, plus 3x to the 5th. Let's just start taking derivatives. Let's see if we can go down to the 4th derivative and then evaluate at 0. So 6x minus 15x squared plus 28x cubed, and then this is going to be 15x to the 4th. I may have gotten in over my head without a calculator here, but we'll try to impress you. 6 minus 30x, 24, 6, 7, 84, right? And then 4 times 15 is 60. X cubed. Doing okay so far, but these numbers are going to get big pretty quickly. 0, so we get negative 30. 184 times 2 is 168x, and then this guy is going to be 180x squared. All right, 4th derivative, we're just about there. Very excited for us. 168 because the negative 30 went to 0. Multiply by 2, that's going to be 360x. Oh, look, if we substitute in 0 here, we do actually get the right answer, don't we? That is pretty cool. And sure, you could go that way. There's nothing wrong with it. However, which way was less effort? Hey, hopefully you said, oh, just by knowing the makeup of a Taylor series, that's a little bit easier. Okay, so one more. Let f be the function with 3rd degree, so f triple prime of x equal to the natural log of x plus e. The coefficient of x to the 4th in the Taylor series about x equals 0 is what? Okay, well, let's think about how we would make up the coefficient of x to the 4th about x equals 0. Wouldn't it be the 4th derivative at 0 divided by 4 factorial times x minus 0 to the 4th? Yeah, I think so, because this is that x to the 4th they're talking about, and they really just want to know what's the value of this coefficient. So in order to do this, I think we'll need to know the 4th derivative at 0. And you might say, oh, I have to take 4 derivatives of that? No, this is already the 3rd derivative. We just have to take 1 derivative. How exciting. So let's maybe do that off on the side. Again, should have used my space better. So I think my 4th derivative of x is going to be 1 over what was inside times the derivative of what's inside. Derivative of x is 1, derivative of e is 0. Cool. And then what is the 4th derivative at 0? It's going to be 1 over 0 plus e. So I think the 4th derivative at 0 is just 1 over e, isn't it? Nice. All right, well, let's clean this guy up then. The 4th derivative at 0 is 1 over e. Okay. This is over 4 factorial, x to the 4th. Think of this as being over 1. Skip, flip, multiply, right? Make your elementary and middle school teachers happy. 1 over 4 factorial times e, x to the 4th. We have found the coefficient. So, nothing too terrible. Usually those are in the form of a multiple choice question. Oh, hey, look, a multiple choice question. What's the coefficient of x squared in this series given below? Very exciting. You'll just need to set up the 2nd derivative, divide by 2 factorial, and you'll be doing just fine. Actually, the rest of today, because the lesson is pretty quick, is all about some multiple choice practice. You need to take away two things from this lesson. First, Maclaurin polynomials are Taylor polynomials, Taylor series, centered at x equals 0. And in fact, you need to know 4 Maclaurin polynomials. You already know 3. 1, 2, and 3. All right, we'll learn the last one maybe next class, maybe not. The second thing you need to take away is how to analyze a specific term of a Taylor polynomial, and that's that. So thank you so much for all of your hard work. I'm excited to keep guiding you through this power series unit. Again, it is my absolute favorite, not to say that there aren't other good units too, but it is my favorite, so keep staying positive. We got this. Keep it up. I'll see you next class.